Okay, so before we started deploying Cosmos, we're thinking about what can it be applied for, and one thing is cloud-connected vehicles in smart city intersections. So Columbia University has not too high rise, and high rise is really 12 or 14 floors. So we're thinking of various ways of monitoring the intersections. So how can we use Cosmos for? Anyway, what we're counting on ultra-high bandwidth, very low latency, and edge computing capability of Cosmos, and smart city and connected vehicles. So that's the domain, and we've tried to play with different applications, one of them being cloud-connected vehicles. The argument is as follows. So today, if we think about Manhattan, it is a fairly complex traffic environment. And then the question is, if we have autonomous cars as we understand them today, like Elon Musk has it, it's a fully autonomous car. Is a fully autonomous car going to be able to run in Manhattan? And we posit that maybe it is not going to be able to do so, but the city infrastructure is going to have to contribute in some ways or means. So that would be a case for cloud-connected vehicles. So thereby, we started thinking of experiments on the Cosmos testbed. What we would, down the line, be able to connect is a fleet of vehicles which would not only have sub-6 gigahertz, but even millimeter wave type of communications. We count on edge computing resources, even this pilot right now on the corner 120th and Amsterdam Avenue, and whatever we could do in the cloud, whether it's edge cloud or the cloud away from the local cloud, sort of comes into the play as well. So we're interested in real-world traffic and networking conditions. So it's a traffic with vehicles and traffic with the communications as well as networking conditions. Essentially, could we support automated driving by a larger number of vehicles in environments where you have many vehicles and you have many pedestrians? What will we need to, what do we think you may need down the line? First, each vehicle has its own sensors, cameras, LiDARs, ultrasound, GPS. Maybe each of them can contribute their own sensor data into this edge cloud, whether in a raw form, which might be video, or some sort of feature extracted form. So you do some feature extraction in the vehicle, and then you upload that into edge cloud. And then what is the other infrastructure? What are the other sensors? The other sensors could be street-level cameras. You've seen the street-level camera in the previous presentation. Bird's-eye cameras in environments such as Manhattan. And whatever other sensors may be attached to the street furniture, buildings or so on. You have to do some sensor fusion. And these days, it's a lot about automated processing, maybe deep learning or artificial intelligence in the edge cloud. So one of the reasons to do it, a couple of reasons why to do it in the edge cloud. Because one of them is sort of very important. It's about privacy, security. You know, how much do you want to push outside? Maybe you don't want to push anything. Maybe only the features are the ones that will be going upwards of the edge cloud. You know, we have a good reason to try to deploy fairly powerful computing resources in the edge cloud. And down the line, you really want to have real-time computation capability if you were to somehow affect the traffic in the smart city. It's sort of a tall order, lots of real-time computing with very small delays. But and Cosmos is supposed to be able to provide us both with very low latency, So not only monitoring, but maybe providing some feedback, potentially controlled to these vehicles in a smart city. Okay, so this is the deployment as it's gonna, so what we have right now, this is Amsterdam Avenue, this is 120th Street, this is the main engineering building at Columbia. The camera that you've seen from the previous presentation is on the second floor, looking upwards, northbound on the Amsterdam Avenue. We have another one on the first floor, looking sideways east-west on the 120th Street. And we're putting two more cameras on top, on 12th floor and 13th floor of the MUD building. And while mentioning the top floors, these bird's eye videos are sort of interesting. And you know, the deployment of Cosmos was happening now, but for the previous year, I could do whatever I wanted to with to do with GoPro cameras. So send students up there on the 12th, 13th floor, taking multiple videos, simultaneous videos, and experimented. I was experimenting with that. And then we'll install 2 more cameras, essentially in apartments of one of our faculty members and one of our students. So that's the idea. Okay, so we had the first space vehicle launch. I was personally involved in it, and Gil gave me some credit. I was hoping to be a pilot, but I wasn't a pilot. The main motivation was I've learned how much we pay these people who do work for us to install these stations. So I put a helmet, and I climbed up into this thing. I didn't realize how high it goes. So as the pilot, there was a guy who is the pilot. So how heavy is this thing? And he said, well, it's 3. And I was thinking, 3 what? I mean, it's not pounds, it's kilograms, I think, he told me. I'm thinking, no, it's probably tons, but doesn't matter. Because this thing down here has to be really heavy if you don't want to fall down. Anyway, I installed these cameras. That was the first vehicle launch. It was sort of exciting. So I want to remind you some of the numbers because we have to be very careful. Some of you who were involved in 4G have heard the concept of tactile internet or whatever, tactile internet. So the idea was, one of the researchers said we would like to have in fifth generation, actually, for 5G, 1 millisecond delays communication. To be really, really careful with that, because if you multiply 1 millisecond with the speed of light, which is 3 times 10 to the 8th, you're going to come up with 300 kilometers. So you're never going to have communication between China and the United States with 1 millisecond delays. You always have to sort of check those numbers. There are a few more numbers that I'm interested in the context of the smart city. If you're driving a car at 100 kilometers per hour, it's about 60 miles an hour. That turns out to be about 30 meters per second. Okay? Now, in a traffic intersection such as the one that we showed, we're speculating. How fast are these vehicles going to move? If I have 15 of them and they have to turn left or right, well, I don't know. But let's imagine an example, 30 miles per hour. That's sort of on the high end, maybe. That's 15 meters per second. Or maybe they're all stuck and it's only 6 miles per hour, in which case I'm dealing with 3 meters per second. So why am I putting these numbers here? Because the video frame rate, most often, is 30 frames per second. So if I'm moving at 3 meters per second, and I have 30 frames per second, it means that I have about, in one video frame, I cover the distance of about 0.1 meter if I'm dealing with 6 miles per hour, or half a meter if I'm dealing with 30 miles per hour. So that's sort of important. You're trying to think, if I do this thing even sort of in real time on a per frame basis, is it useful? Does it matter? So maybe if these vehicles are moving really slow, I don't know. And we've heard Ritwik's presentation. He was really careful to tell us when he talks about AT&T network, don't really focus on real time. Real time is really, really hard. 1 millisecond is really, really hard. Focus on near real time, which is 10 milliseconds above. Well, maybe you don't have to consider AT&T network. This is an edge cloud. Maybe we can do things a little bit faster. So maybe we can do real-time stuff within 1 millisecond, 5 milliseconds, maybe, on all levels. Deep learning, video collections, sensor fusion. If we can do that, that would be useful. So we would like to experiment with all of that. Just try to run the experiments to see what's doable. So this would be just yet another video. This is the 4th floor. The only thing I want to illustrate to you, I'm a communications engineer, so bit error rates mean a lot to me. So if something has an error rate that is worse than 10 to the minus 5, it sort of doesn't work. So when I see these deep learning models and they show us that, let's see if this is going to run off the, okay, maybe not, doesn't really, okay, it will. Huh? It will run, I think. So even if it doesn't show, what I want to tell you is that many of these deep learning models, they supposedly work fine, but the error ring is quite high. It means you track a vehicle, and it's identified as vehicle number 11, 11, 11, 11 for the first 35 frames, and then becomes, yeah, I see it on my screen. I don't see it here. Okay. What do you say? How do you do that? What do you move to the right? Oh, I just don't see it on my screen, I guess. It's not that important. What I want to say is that this vehicle might pass behind this traffic light, and it suddenly becomes, rather than vehicle number 2, it becomes vehicle number 6. That's a problem. So what I'm working with the students is I would really like to improve through some sort of diversity techniques that we are using in radio, so to apply them to some sort of video processing at various levels, at pixel levels and above levels, to reduce the erroring rates. So that's sort of a little nice, meaningful research project. It's actually very hard, but it's a nice problem. So we can skip it.
I have it, but...
Okay. So what's going to happen, for instance, this truck is a 13 and becomes something else. And then there's going to be one more vehicle, it probably already passed, right here, so it disappears for a while. So I'm thinking that's completely unacceptable. And you get, for these types of systems, it really has to work well. So that's where we're spending some time on. Do you press escape, or what do you do now? Okay. Oh, it's interesting that the mouse doesn't react.
There you go. Yes.
Okay. The other problem that you have when we work with these systems, how do you evaluate how good the system is? So imagine you're doing the tracking of vehicles. So these deep learning models very often either rely on these boxes or on segmentations of vehicles. If you're trying to establish a trajectory, you sort of find some center, either of the box or that segmented vehicle, but it's very noisy. And each of these different models has different performance. Now, for me to be able to judge how well they work, I need some sort of ground truth. I need the real situation. It's actually really, really hard to acquire the ground truth. So we've come up with at least 3 different ways of coming up with the ground truth. The most prominent one being, we have pizza parties for the whole day, and we annotate, I don't know how many polygons. That's the because of pizza, it's very favored by students, but for other reasons, they hate to do it. But all the students like to work on deep learning, so this is part of the job. I tell them that's the first thing. You don't get to do anything else. The other thing is building the ground truth. Those of us who are in sort of signal processing, image processing, we're familiar with traditional type of stuff. So what I did, I took my van, I put a huge orange circle on top of my van, and I rode for about 2 hours, and they were taping me. And then I say, well, forget about neural networks. I just do traditional signal processing, convolutional matched filtering, and catch the center of that round circle, and I build the ground truth for whatever, 17 minutes or out of those 2 hours. And that becomes my piece of the training for these neural networks. And there may be other methods as well. This is the, okay, let's see, let's press once again. I'm not going to try to run this video, but what I found appealing, certainly in New York City, is if you go to the 10th or 12th floor, you have a pretty good view from the top. Contextually, it's better than when you're looking from the sides. And again, these models that you get off the shelf, they sort of work, but they have fairly high failure rate because of very small pedestrians. So again, how do you improve that? So that's another part of work that we do. One thought that we had, what could be the first useful thing we can do is just take, for the moment, rather than considering sensors from the vehicles, at the beginning, just look at the bird's eye cameras. As soon as we can, we also take all other sensors. But we fuse all of that data, and we extract the features. What may be the most important features is just velocity vectors of all participants in the traffic intersection. So these blue and purple vectors are just velocity vectors of vehicles and of pedestrians. So we create these vectors, whether it's by combining the sensors from everybody or just from bird's eye videos, and then we say, okay, we transmit that to all of the vehicles. And imagine that in every vehicle now you have on your front screen or whatever, you sort of understand what's going around the corners as well. So that may be the next experiment we'd like to try. So I'll stop here. That gives you an idea, but probably the thing is that anybody who wants to work in this space, if we build this capability, we can acquire these videos, we have enough processing power, we can deploy different types of software, we want to play with real time. we'll be able to do, we're planning to create a platform that would support that. And this is just an example of maybe one such experiment. I call this, learn the radar screen and ultimately broadcast the radar screen to all the participants in the traffic. And potentially alert the pedestrians, what's going on around it. Is somebody going too fast? Are you going to be hit by somebody? The phone is gonna shake or whatever. It's gonna. How does it work at night? Well, we have thermal cameras, I guess. Yeah, we don't, but I've learned how to pilot those. As I said, we'll install different cameras. The challenge, there is a bunch of challenges. For the bird's eye views, the small pedestrian, which you see only from the top, is quite a problem. So you have to figure out how to deal with it. Sideways facial recognition is actually much easier. You have lots of systems that do that. Again, measuring the quality of estimation, that's one of the things that I'm really trying to figure out. First, what is the reference, what is the ground truth, and then what is the right measurement for that. I didn't even touch really the data aggregation and fusion, and all sorts of problems with these deep learning techniques that, again, as a communication engineer, until it gets to 10 to whatever, -3 of erroring, we're not anywhere, in my opinion. So down the line, maybe you deal with prediction. I first estimate the trajectory. Maybe I can predict a couple of frames ahead. That's, visionary, I guess. And the key thing to all of this, low latency communication. So maybe pieces of this will be able to demonstrate. That's where I'm going to end.